Hi, I'm Evan Owen, startup founder, software engineer, and AI researcher. This is the story of one kernel from my GPT-2 port to Mojo, and how the math wrote its memory schedule. This one line computes the gradient of LayerNorm's input. It is the last line of the backwards pass in my project llm.mojo, GPT-2 training in pure Mojo. Every kernel I hand wrote for the CPU and GPU. 1 over sigma times g times dy minus s sub 1 minus x hat times s sub 2. That first bit is the chain rule. The other two terms look like they shouldn't be there. In the next 4 minutes, I want to show you where they come from and how that answer decides the parallelization of this kernel. LayerNorm does two things to a row. Subtract the mean, divide by the standard deviation. Where the row sat and how big it was are gone. So when a gradient comes back through, 2 requests are wasted. If you shift the whole row, the mean subtraction undoes it. If you stretch it, the variance division undoes it. So backprop deletes exactly those two pieces of the gradient. The part that shifts the row and the part that stretches it, keeping only what the output can see. This is known as a projection. Written out, u minus the mean of u minus x hat times the mean of u times x hat. Those two means are s sub 1 and s sub 2. The terms that look out of place. Here's the part of the math we care most about. A projection needs 2 dot products, and a dot product doesn't produce a number until it has seen an entire row. So the kernel physically cannot write a single output until it has read every single input. 2 passes, not just one. This isn't a choice that I made. The math wrote the memory schedule. Pass 1 is the 2 dot products. They're SIMD accumulators, so every lane carries its own running partial, and the whole row collapses with a single reduced add at the end. That is the first thing you get for free. A sum is the friendliest possible thing to vectorize. Pass 2 applies the projection. S sub 1 and S sub 2 are the coefficients. The same line you saw at the start. And rows are independent of each other, so the outer loop is just a closure over a slice of rows handed to trace parallelize. The closure captures the pointers directly. No argument marshalling, no thread pool boilerplate. A closure and SIMD lanes, nothing exotic, and it's 5 times faster than llm.c with OpenMP across 16 threads. Now, let's look at the same kernel on the GPU. Look at the middle section. That's the same code. The math doesn't know what hardware it's running on, so the arithmetic doesn't either. 2 things change. How rows get handed out. A worker slice of rows becomes a block striding over rows, and how the partial gets reduced. Reduce add across SIMD lanes becomes block sum across threads. Everything between those two is shared. That's the argument for writing kernels in Mojo. Not that it's fast, though it is, that one expression of math can carry 2 schedules. Here's the real training. llm.c's canonical 40-step run, batch for batch. Watch the validation loss land. It matches llm.c exactly to 3 decimal places. And that's one op. 25 more like it in the repo with the full math of bat propagation. All MIT license, the link is on the screen. Thanks to Martin Dudek for the original Mojo port, Andre Karpathy for llm.c, and 3 Blue 1 Browns Manum for the animations.